thus ozone does trap heat in the atmosphere. In fact, this heating or the trapping of irradiation by ozone is evident in the temperature increase that you find, or the temperature between 8 to 15 kilometer in the Earth atmosphere is maintained because of this absorption of the infrared radiation by ozone. Now, suppose if the ozone decreases in the stratosphere, then it will actually lead to surface cooling, while increase in the ozone in the troposphere will lead to warming. In addition, ozone is important because it is a key ingredient that initiates chemical reactions in the Earth's atmosphere and resulting in chemical cleansing of the atmosphere of various pollutants, namely carbon monoxide, which is harmful, which is again emitted from the tailpipes of vehicles, industrial emissions, etc. The nitrogen dioxide, nitrogen oxides, again, and methane is emitted from natural and the man-made sources. Now, these gases, suppose if ozone is not present, will accumulate to harmful levels, and because of their radiative properties, can actually exert a more stronger influence on health. As a result, any increase or decrease in ozone, be it in stratosphere much above our head or in the troposphere, which is very nearby, induces or it affects the climate, thereby establishing a link, a direct link between changes in ozone to climate. So, how is ozone produced? What is the source of ozone in the atmosphere? Ozone is actually a naturally occurring gas that is produced mainly in the tropical upper stratosphere through pure oxygen photochemistry. So, first the oxygen molecules get split up into two oxygen atoms, and then which again recombines to form the ozone with the wavelength of radiation that is lower than 242 nanometer, which is in the ultraviolet. So, once it is produced, so please note there are two important points here. One is it is produced in the upper stratosphere and in the tropics. Once it is produced in the tropics, how is ozone formed in the other groups? The contribution of the production is maximum in the tropics because the amount of solar radiation that we receive in the tropics is higher than what we see in the mid and the high latitudes, including the poles, and the oxygen molecules then interact with this radiation, which take up and then form the ozone. Hence, the amount of ozone that is produced in the tropical upper stratosphere is more. Once it is produced, because of the transport of the winds that take away from the species that is produced, this is actually transported. The ozone that is produced in the tropics is transported across the other regions of the world. So, this the ozone that is produced in the tropical stratosphere, it goes up and then gets moved to the other regions, and then it sinks over these particular latitudes, namely the higher. And we will see as the lecture progresses that what is happening over Antarctica when there is the ozone is getting depleted or is getting decreased. So it goes up, the ozone that is produced here travels all the way to both the hemispheres, but then you see that there are conditions that exist that actually decrease the ozone in the high latitudes. So how does it look? According to as a function of season and time, and also as a function of the latitude and longitude. So what you are seeing here is actually the scale is from right, and it is the total ozone that is present is represented here, which is in the name of what is called as the Dobson unit. This is in honor or memory of the scientist who actually developed an instrument to measure the ozone concentration. And in memory of these, as it is normal in the science parlance or the science community, to name the parameter or the instrument that was discovered by the scientists who did this. For example, the scattering by air molecules It's named after Raleigh or Lord Raleigh, who found this. And mainly, for example, go to the Indian things, so CV Roman effect, etc. In the same way, it is the unit that with which we use to measure the total column ozone is named after Thomson. And here what you see is the global map of the total ozone that is present in the atmosphere during different seasons. So what is immediately clear is that ozone does exhibit latitude, longitude, seasonal and zonal variations, and it will also exhibit interannual variations as we will see in the subsequent period of the growth. Now, why it should exhibit geographical variation? Now, this is because of the variations in the air motions and the mixing of the ozone that is produced in the tropical stratosphere getting transferred or transported to the other regions, etc. And also the changes in the balance of chemical production and loss of ozone as air gets transferred. So typically the residence time of ozone varies from a few hours in lower altitude to about weeks to months in the stratosphere, in the lower and upper stratosphere. So the balance of ozone, the amount of ozone that is present in the atmosphere is actually maintained by a balance between the production and loss, which depends on the amount of sunlight that is available, is present. So, okay, ozone is produced now. How does it get depleted? Why ozone should decrease or deplete? So, the principal steps that are involved in the depletion of stratospheric ozone are this occurs because of the halogen source gases that are emitted at the Earth's surface by human activities and natural processes. You will see the bifurcation of natural and man-made process these halogen source gases. Now, these gases accumulate in the atmosphere and they are distributed throughout the lower atmosphere by winds and the air motions. Now, can't they get removed here? I mean, like, for example, rain coming in and then taking away these gases? The answer is most of it they have very long lifetimes. Chlorofluorocarbons that we emitted, which are being used in a variety of industries, including refrigeration, shipbuilding, foam, construction, etc. So they all have lifetimes depending on which species they are. They have lifetimes of about 60 to 100 years. So, and these are chemically inert. Chemically, they don't react in the lower order. These are heavier than air, but then they get transported across to the higher altitudes by the circulation, both in terms of vertical as well as in the latitudinal. Once they reach the stratosphere, they get converted into what is called as a reactive halogen gases. This occurs with chemical reactions that involve ultraviolet radiation that sun. Once they become reactive halogen gases, they can deplete ozone. In all regions of the globe except at tropical latitudes, because we are the production of the source region and the production and the loss, production overwhelms the loss. So the loss in ozone is actually not significant tropical belt, meaning between 20 degrees south of Earth's center. So in addition, there is one more phenomenon which we will see in the next few slides. There is what we call here, we are familiar with clouds that represent in the atmosphere, which you can see outside the window, which are like cumulus, stratocumulus, nimbus, etc. But in the polar regions, there is another phenomenon called polar stratospheric clouds that occur in over the altitude regimes. They occur at very particular conditions, very particular time frame, when all the conditions are favorable, and they actually contribute to the decrease in the ozone. Now, once we are there, I said these are long lifetimes. So, how do they get removed? Once after the depletion is over, after so many years or so, they actually will start descending down to the Earth's atmosphere, where they get moved by the air from the moisture. Now, how was ozone in the past? So let us say, let us go back by 60, 70 years from now. You see that this is in the southern hemisphere. We'll also see later northern hemisphere. So the scale is the same in Dobson unit. The graph color is also the same. It is varying from 100 to 60. So this is Antarctica. What you are seeing is actually the continent of Antarctica. And from year 1970, so you can see that the more reddish hue is slightly in in 79. Now you see that the entire continent of Antarctica is actually having ozone that is much lesser than 200 Dobson. Please coordinate the color scale. You will see that what was there in green here, which was the excess of about 300 Dobson unit. Now the scenario is the same even now in 2020, which you will see in the next 2 or 3 slides. So there is a huge decrease in the ozone is present over the Antarctic, and please note that decrease is not only restricted to Antarctic but also the regions that are surrounding Antarctic, which is much bigger, as you can see in this figure. Now, so I mentioned that there are halogen source gases that contribute, get converted to reactive halogen gases, and so you see that these are the amount of halogen source gases that enter the stratosphere. On the left column is the total fluorine amount, is present in parts per trillion, 1 in 10 to the power of 12. So these are these gases, or the concentrations of these are very small when compared to, let us say, air molecules or even ozone, for example. But the kind of damage that these gases do to the human life and its existence on Earth is tremendous. Orders of magnitude high. So these are produced by both natural and the man-made sources. Human activity contributing much significantly. And you are also seeing, for example, the changes between 93 to 2016. Why 93? Because that was when the chlorine concentrations in the Earth's atmosphere. With respect to that, the implement of the convention protocol to use the chlorofluorocarbon substances, ozone, etc. There have been changes, there are reduction. Still, the concentration is significantly high and now. So between so there is a change in natural, much of a change. But you see that these gases that are present in the atmosphere, depending on their lifetimes, yes, there is a reduction of percentage. It is the same with respect to bromine also. Let's say chlorofluorocarbons, we are referring to the chlorine, bromine, and ionic substances or the compounds that combine to form what is called as in total the chlorofluorocarbons. So if you look at the total chlorine, the scales are here. With respect to bromine is roughly about 150 times more. So the chlorofluorocarbons that are present in the atmosphere and actually the most abundant ones are the chlorine-containing gases. But in terms of the depleting potentials, bromine will be much higher compared to chlorine. So this is again illustrated here, the kind of halogen source gases with the chemical reactions that occur with the amount of sunlight, ultraviolet sunlight that is available. They get converted into reactive halogen gases, and these reactions, they occur on the stratospheric clouds, which we will see next. And then they get converted to reservoir forms of reactive chlorine gases such as ClO and O2 and the hydrogen chloride. And then the most reactive form of this is ClO, which is very efficient in chlorine chloride, which is very efficient in depleting ozone. So one of the cycles I am showing here. So we saw that the ozone molecule is produced by the reaction involving oxygen molecule and ozone gets produced, and this chlorine monoxide, the ClO, which is a reactive form of CaO2 or the hydrogen, right? That is converted because of the from the halogen source gases to the reactive gas. They can in this reaction you can see what is destroyed is so the ozone that is produced by oxygen molecules in an atom gets depleted because of the chlorine monoxide this in this fashion. And please note that I have named this as the chlorine catalytic cycle because in the whole reaction, chlorine does not get destroyed. It survives as a catalyst, and then it can keep continuing to deplete ozone till it loses certain amount of energy and come back in the lower atmosphere, and then gaining the energy, go back up, and then start to deplete ozone. And that is why the species that have been already in the atmosphere, because of their long residence time, because of this catalytic process, they can deplete ozone long after the production has stopped. So I did mention about the clouds that form in the higher altitudes, maybe the polar regions, which we call as the polar stratospheric clouds, which is nothing but the nitric acid, HNO3 and the water which condense on the pre-existing sulfur-containing particles. So these sulfur-containing particles are nothing but familiar aerosols, solid or liquid particles that are present. But in terms of the number, it is very, very small. The number of sulfur particles in those altitudes. The temperatures in the polar regions are much lower, meaning minus 78 degrees centigrade, which is in terms of Kelvin is 195. So if you look at, so this is one example of how the polar stratospheric clouds look in the polar regions, which looks definitely different than the clouds that we are right now seeing across our window in the lower altitudes. So what we are seeing is the variation in the temperature between May to October in terms of the Antarctic, because it is the southern hemisphere, and between November to April, the Arctic, which is the northern hemisphere. And what we are looking at is the range of temperature, the temperature values, those were measured during the last 50 years over both these regions, namely the Antarctic or the Arctic. So the black perpendicular line that you see represents the temperature of minus 78 degrees centigrade, below which the meaning values that are lower than minus 78 going all the way up to minus, right? The polar stratospheric clouds will form. These are the perfect conditions for polar stratospheric clouds to form in these latitude regions or the high poles. And so here we are seeing graphs in blue color represented by the shade gray, and also the line in red with the yellow shading. So the blue one represents the Antarctic temperatures, the red one represents the Arctic temperatures. This time frame when the ozone gets depleted in both the hemispheres, but in different times. So it is immediately clear that temperature can be lower than minus 70 degrees over Antarctic for more than 6 months a year. These values are lower than minus 70. But in the Arctic, it is not that severe. The temperatures are lower only for 2 months during the Arctic. Keep that in mind as the thought process. So, when does, first let us begin with Antarctic ozone hole, and then we will move on to Arctic. Why it is called a hole, I will describe it in the next few minutes. So, for example, what you are seeing here is the conditions in May, particular year, at around 18 kilometer altitude, which is the region where the ozone is depleted. So, the color bar is the same that you are familiar with. Here you see that the ozone abundances. Here in terms of the abundances we have now seen. So here, so I am now concentrating the graph on the left panel, which is the Antarctic is shown in the black curve here, You see the ozone values are very high, which is red. This is in May 2000, May of the year, particularly. You see the temperatures are on the order of about -60 centigrade, which means that it is still not temperatures that are good enough to form the polar surface clouds. And you also see hydrogen chloride that is high, but then does not become the reactant to deplete ozone. Nitric oxide is also high, chlorine monoxide is very, very low. It's all entirely purple. So these are low concentrations. Now contrast this with September, in the day, like today, for example. If you look at it, we are looking at, imagine that this is a scenario that was yesterday over the Antarctic. So you see that first, that curve is actually defined purple, where the ozone concentrations are decreased enormously from what it was to here. So from about 280 parts per minute or 2,800 parts per billion volume of ozone, it's now become almost less than even 18. It's about 1,000 parts per billion ozone molecules decrease. Now look at the temperature, which is much lower than -60 centigrade we saw. And then you also look at the chlorine monoxide content. These have increased hugely from nothing to maximum scale that we see. Now, why? The immediate question is, why does it occur only over Antarctica? Why doesn't it happen in other places? So we know the timing that this will occur in late winter and early spring. The abundant reactive halogen gases there, and then the temperatures are low enough to form the polar surface clouds, and the air that is present over the Arctic is isolated from the other air that is present in the atmosphere, which we call is a kind of a vortex. So imagine that this region is actually kind of bottled up. In a bottle, you have this air, and that contains a large amount of this chlorofluorocarbons. And then once the sunlight begins to form, as we know that it is 6 months of darkness, so once the sunlight starts falling on the Antarctic, all these conditions, including the polar vortex, helps making the ozone depletion reactions to take place faster, and you can see the change that happens for this Antarctic region. Now, coming to the present, as of today, this year, what has happened to the conditions of ozone in the Arctic? So far we looked at, for example, the 50 years of change and the conditions of change that are required ozone in the Antarctic. And now coming to the present year, 11 June 2020 to 11 September, 3 months time, you can see that the ozone is the same color coding. You can see that there is a huge decrease in the ozone that is present over the Antarctic, and you can also see the white continental map. And so, what has happened? How does it change on a day-to-day basis during this particular year? So, to begin with, in July, so this what you are seeing is the ozone hole area, which we'll talk about in the next transparency. In the area where the ozone values are lower than 220,000. Why 220? I will tell you. See. So now, when the ozone decreases, so from in July, it started in July. On July 1st, the ozone there was no depletion, so that is why it is represented as 0. And then as you come across, going all the way up to September, for example, see that the area in terms of millions of square kilometers has increased, this is 24 million square kilometers. Compared to the size of the Antarctic continent, this is even much, much larger. So, how much the ozone has decreased from the value of 233 in July to now? This is roughly 141,000. So you can see the huge decrease in the ozone value as we saw the previous transparency. So What about the stratospheric temperature for the polar stratospheric clouds? The temperatures were to begin with, so we said that under 95 Kelvin is the main value for the stratospheric clouds. You can see that the values were lower and then they start decreasing. Once later in October and November and all, they will the temperatures will increase, and so the ozone depletion will also come down, as you can see. The values, the white curve and the gray shaded curves indicate the averages of decrease of the increase in the ozone the last 50 years or so, starting from 1980. So the ozone, for example, we looked at how the ozone hole or the depletion is much higher than the size of the Antarctic continent, which is now, this is actually about 25 million square kilometers. That is roughly twice the size of the Antarctic. And we call this as ozone hole and not say decrease or depletion or decrement or something. We call specifically this as ozone hole. That is because if you look at the ozone values from high above, and you look at the concentration of plot the concentration on the globe, you will see that the ozone values increase as you go over the Antarctic continent. It will actually look like a hole in the concentration, and that is why the increase in ozone over the Antarctic is called as the Antarctic ozone hole. And what is the value that corresponds to the called as the ozone hole? It is when the ozone concentration in Dobson unit is lower than 220, then that is actually called as the ozone hole. Now, the immediate question is, we talked about Antarctic and we also said that, well, it happens in the Arctic also. So, is there a comparison? Is the same thing happening in the Antarctic? So let us look at the difference between Antarctic and the Arctic. So, for example, on the first panel, you see as a function of the altitude, the ozone concentrations. The initial in 62 to 1971, with the same measurement method, flying balloon to measure the ozone concentrations. You see that this was the concentration in 1970. But now look at the recent past 30 years or so, the ozone from blue, green is nothing, almost as I mean, everything has been washed away. The decrease is very, very significant. And among these years, if you look at the lowest that was ever measured, look at the curve in red, which is on 9th October 2006, you don't see any ozone at all over the Antarctic. This is almost zero. Now, contrast this with the Arctic, for example. Ozone has depleted with respect to the last 50 years or so, but then the depletion is not as significant as you see in the Antarctic. Now, why is it that there is a difference? I mean, same pole, one is located in the southern hemisphere, the other is located in the northern hemisphere. The ozone gets transported, the temperature, both are cold, the temperatures are lower, etc. Now, the question is, there is the fundamental difference between the amount of ozone that is present over the Arctic and the Antarctic. The average level of ozone in the Arctic is higher than what is found in the Antarctic. So if you look at the average levels of ozone in the Arctic, this is on the order of about 450 parts per billion by volume, while in Antarctic it is less than 300. So when you compare the values, so the Arctic values are inherently higher than what you have in Antarctic. Now, the other change that occurs in the northern hemisphere, said ozone is produced, it gets transported and all that. So the ozone gets transported to higher altitudes, then which goes to the higher latitudes and then sink into the high latitude regions. Now, and the downward transport of ozone air, rich air, is stronger in the northern hemisphere when compared to the southern hemisphere. So the amount of ozone that is present in the northern hemisphere is higher than what's present in Antarctica, which is in the southern hemisphere. Now, the other, so we talked about polar stratospheric clouds and the particles that are present in the atmosphere can actually decrease the ozone through what is called as the heterogeneous chemistry, because the species that are involved includes gases. These reactions of ozone depletion occur on the solid or the liquid particle, which is the sulfate particles that is present, and then which produce chlorine, the highly reactive species, namely the chlorine and the nitric acid, which then also result in the active form of chlorine, reactive form of chlorine, namely chlorine monoxide, and then ozone depletion takes place. So whenever there is a volcanic eruption that occurs, the ozone depletion will also occur. As you can see here, for example, there are two natural causes that could contribute to change in ozone. One is the incoming solar radiation itself, which is the prime driver of the solar system, and the other one, natural cause, is the volcanic eruption. So what we are seeing in the top is the incoming solar radiation for the past 60 years or so. It follows a 11-year-old seasonal cycle, as you are all familiar. Changes are cyclic, which is solar maximum, solar minimum. Then you see the cyclic periodicity of the solar radiation. Compare this with the decrease in ozone that we have seen in the last 60 years. Now, you can see that these changes cannot accommodate for the decreases is what you see as the global ozone changes. Now, what is plotted here is the change in the concentration due to the volcanic eruptions in the last 60 years. So these values are zero. Any dips indicate increase in the amount of aerosol particles due to volcanic eruption. You see that these are also kind of happening in about once in about 10 years in the past 40 years, and none of them are able to account the gradual decrease that is happening. So, if there is a volcanic eruption and the aerosols that are produced as a result of the volcanic eruption, ozone will deplete. As you can see here, as it happened just after the last eruption, which was Mount Pinatubo in 1991. But, however, the gradual decrease is actually not being explained by both natural causes of variation, which is the cyclic variations in the solar radiation and also the volcanic. This can only be explained by the abundance of the chlorine in the bromine molecules or the species that are present, which is represented here in terms of the equal effective stratospheric chlorine. So what you see is that clearly anti-correlation. The depletion of ozone corresponds to the increase in these gases, and then ozone will try to become better as soon as the concentrations of these. So the long-term increase or the change in ozone can only be attributed to the increases in the chlorine and the bromine substances that are present in over the same time period. So, is the ozone depletion global? The answer is yes. But however, in the latitude, in the tropical latitudes, as I mentioned earlier, the changes are very less when compared to what is happening in the higher latitudes, namely the southern and the northern. One of the effects is one of the participants now asked a question as to the ozone anyway is decreasing in the high latitude, so why does it concern us? So this can, as we know that the reduction in ozone can contribute to the increase in the ultraviolet radiation. That can, so the observations do indicate that the surface level ultraviolet radiation has increased. So our exposure to the ultraviolet biologically active radiation has increased, leading to erythemal, which is actually the sun burning issues, and then the surface level erythemal ultraviolet radiation has actually increased in the last 40 years. The clouds and aerosols, clouds that are present here in the aerosol particles, can offset the increase. But however, if you take the total summation, still the average change is still negative. It's one of negative. The cloud and the aerosols can only change a little bit with the ozone, but so on an overall sense, we still are facing the effect of decrease in the ozone. So the immediate question is whether with all these reduction, when is it we will get to the future, which will be the same as the past in the last 40 years or so. Whether ozone concentrations, when it will come back up to. So these are some of the estimates, observations, the projections of the gases that depleted ozone. So as you can see that all these gases, they are all in parts per trillion, and then the abundances were increasing in the last decades, and now they have started showing decreases. They started happening around 1980. So, and then these are projections that they will actually reach the levels in about 60 to 80 years. So these are as far as the man-made contributions and emissions that happen and the changes that will occur. These are now the ozone hole, for example. Is it uniform that will occur every year at this time with the same magnitude continuing to happen every year? The answer is actually yes or no. So what you are looking at is the ozone hole over the Antarctic during 2 years, 2001 and 2003. They look more or less similar. Now, what happened in between the year 2002, for example, which is very starkly different than the years preceding and succeeding years. So what happened was initially the hole was circular, but then it got split into two depleted regions of ozone. So you can see that, for example, here the whole Antarctic there was a blue shade, but here in 2002 you don't see this. Now this was caused by the warming of the polar stratosphere, which is actually detrimental or against for the formation of the polar stratosphere clouds due to the meteorological disturbances of the variations that originated in the troposphere at mid-latitude. So the air in the mid-latitudes get transported to high latitudes. This actually was warmer, and then it tries to increase the temperature, thereby decreasing the polar stratosphere. So warmer temperatures will reduce ozone depletion, meaning the loss is less, as it happened in 2002 compared to 2001 and 2003. This variability in the ozone depletion is entirely attributed to the natural causes, which is the change in the dynamical ecological disturbances. Now, coming to the ozone that is near Earth's surface, namely the stratosphere, we know that it occurs through oxygen photochemistry, while in the troposphere, this occurs due to what we call as the bad ozone. It occurs due to, it is not directly emitted into the air. It is created by chemical reactions between the various oxides and the volatile organic compounds in the presence of heat and sunlight. From where these nitrogen oxides and volatile organic compounds come, these are from industrial facilities, electric facilities, the vehicles, gasoline, chemical solvents, which are all the forms of urbanization and globalization, which increase resulting in the vehicular industrial emissions and also resulting in smog conditions. So, if you look at the forcing, the changes in the ozone. For example, we are all familiar with changes in the carbon dioxide and the warming that it is producing, as we saw in the initial few slides. You see that this is all highly positive, going all the way up to 2 watt per meter square, but ozone increases in the lower atmosphere is actually contributing to warming at the surface on the order of about 0.5, but decreases in the stratospheric ozone because of ozone depleting substances is actually contributing to a surface cooling. Now, the most important question is, okay, when will ozone be back up to normal? So these are some of the observations in the last 60 years after the ozone started depleting from 1980s, and then when the projection based on the observations and the trends that we have seen in the last few years, and based on the projection, the the models that can simulate very well the ozone and other atmospheric parameters, we see that global ozone will recover to the levels that we saw in 1980 in roughly about 30 years from now. So, provided, which is marked here in red, provided there are no volcanic eruptions and other meteorological variations that we saw in 2002, which contributed to the depletion. So, why so? Because you see that decreases, we saw that the volcanic eruptions can cause transient depletion of ozone. So, we see this is actually 1991 and it is decreasing. So, if Pinatubo did not occur, this would have actually gone like this, which is actually shown in blue. But because of the volcanic eruption, the ozone values significantly went much lower, and then it took about 3 to 4 years for it to come back to the declining gene. So these natural causes can also change the way. So the troposphere, the ozone in the troposphere, for example, it is showing an increase in trend because of the increase in the man-made emissions, which is again harmful for the human being. So, while the reduction in the stratospheric ozone has to be stopped, meaning this has to be, the ozone in the stratosphere has to increase, but in the troposphere it should not increase, because reducing this in the troposphere will actually improve the air quality and will contribute to global warming, as we saw before in the previous transparency, in terms of forcing and the temperature change. So, to summarize, we began with the importance of ozone, the sources and the sinks, how they are distributed in terms of the vertical, spatial, and seasonal scales, how they vary as a function of year to year, and what is ozone depletion, the features that mark what are there in Antarctic versus the Arctic, the constitutive mechanisms, why does it occur there, when, etc., and what is happening because of this, the increase in the surface ultraviolet radiation, how clouds and aerosols are contributing to it, the heterogeneous chemical reactions that occur on the aerosols because of the volcanic particles, and also the remnant particles that are present, namely the sulfate species. And then in terms of the forcing, how the stratosphere, the ozone in the stratosphere contributes the surface cooling, and the ozone in the troposphere contributes to surface warming. And we also looked at some of the future aspects, such as how the ozone will recover, why and how. And with this, thank you for your time. I will be happy to answer questions now.
Thank you very much, sir.
Welcome.
Indeed, it is a great pleasure to get all these insights, which is synthesized by great years of hard work and dedication to understand this subject. Before we move to the question and answer session, I will request Honorable Member Secretary of Gujarat Council on Science and Technology, Gujpos, Shri Narottam Sahu sir, to give his remarks on the occasion of the World Ozone Day. Sahu sir, kindly enlighten us on today's occasion.
Good afternoon to everybody. Am I audible?
Yes. Yes.
Respected Professor S. Ramachandran sir, Setal sir, and all the members of faculties of Climate Change Department, all the panelists, and all our science-loving friends. Actually, आज एक बहुत अच्छा दिन है, बहुत खुशी का दिन है कि आज हम लोग 35 साल का एक जर्नी का आज हम लोग इनका एक महसूस ले रहे हैं, ह्यूमन पावर एंड कंबाइनिंग अप्रोच of everybody can tackle a change, can bring a change. In fact, we are very thankful to Professor S. Ramachandran, the very senior professor of Physical Research Laboratory, Ahmedabad, who is working on this hardcore science of ozone layer and atmospheric science and giving us a new knowledge and a new experience through its outstanding research and contribution. And Professor Ramchandran sir is working directly with many of such international, national and international organizations जहाँ पे वो ओजोन लेयर के ऊपर में अलग अलग ट्रीटी के माध्यम से इनका मॉनिटरिंग एंड इनका मेजरमेंट हो रहे हैं. So we are very much fortunate to have our guest speaker Professor Ramchandran sir on this auspicious days. And as you all of attend this program and his presentation, it's a really virtual journey of ozone layer for the last 35 years from the past, present, and how we will be going to face this in the coming years also. Otherwise, if this program is not coordinated in such a massive manner, I think today we can another world or world catastrophe like this coronavirus or a pandemic virus, which is a pandemic, but it's this global ozone hole. It can be a much better than a larger disaster, we can say. As you have seen from the slide also, a single 1 centimeter hole in that ozone layer, which is protecting or which is absorbing this deadly ultraviolet rays from the sun's radiation, it can create, I think, minimum 5 lakhs of cancer patients in this earth. So 1 single centimeter hole of ozone layer can bring that much 5 lakh cancer patients in our Earth surface. It's a study. It's a reported number also. Similarly, also there is a large number of domestic plant also. So that's the major issue, and that gives a new challenges and a new opportunity for the entire world, entire science streams and entire policymakers. That yes, we solved this ozone layer, or we save this ozone layer. Now we can save our climate too. So this is another campaign and another hope and another mission is going on. How we have to work together from the country level committee of the committee of the parties COP. And COP21 के बाद अभी another series, next series are also going on, and all our policymakers at the United Nations level, even all the heads of the states, member countries, they are working on those things. Unless until we have to devise a clear-cut policy and very stringent procedures, then we can minimize these issues. So the take-home message is that we can, yes, 35 years ago, we have identified this problem, and to the successive missions, successive action plans, and also midterm reviews, and also remedies that have been taken from time to time. Now we are coming to close this whole story. So now this gap gives another hope and our opportunity that yes, how we have to address this climate change problem like that way. We are very happy that this program is being attended by many students, many teachers of our states and out of the state also, which are another few years they can complete their academic curriculum career and being a very responsible citizens. And if they have that type of involvement, that type of participation, that type of support with this type of global issues, then yes, we can go through this climate change problem and climate change scenario also. So I am very happy that Professor Ramchandran sir, despite his busy schedule and his international things, sometimes we may find him here or in the abroad also, in the other countries or other institutions also. We are very lucky that sir is here and giving a very fundamental and a very walkthrough to this journey, so which is very clear, and on that too also scientific explanations of all these stages from year to year and these things. So this remarkable story of this deadly hole, story of this ozone layer, and now we can go ahead in the future how we have to fix that completely fix that one, and also related to these things. But once you sir has mentioned that there was a very significant point when there was a restriction of the CFC, chlorofluorocarbon, and instead of that we have introduced another chemical, H hydrogen chlorine and fluorine HCl, so that it can be prevent that observe that ultraviolet rays there. But now scientists also finding that that have that having that capacity of trapping these greenhouse gases, so that might be adding more temperature to this our earth. So now these types of research is going on side by side. So our scientific community and research members, they are giving the new knowledge, new experience, what to do and what not to do and how to do. And there are the policy makers at the top level, they are implementing this type of things. And the third category is the consumer or the citizens or the community members, which has a great role that how best we have to adapt to that changes. So today's celebration is mostly depends upon the collaborative participation, collaborative approach that everybody from the ground zero to the community members to students, children, to the common citizen, common public, to the policy makers, including the scientists and the scientific institutions, they have to come together and to have to be, attempt this program in a very competitive way and in a very comprehensive manner. So that is the major agenda and major call for this day. So on this occasion, I once again thanks to Climate Change Department and the Principal Secretary, Dr. S.J. Haider sir, for his kind support and kind interest in this particular issues, and taking all the stakeholders together so that everybody can understand the issue in a very clear-cut way and also understand the policy actions to be taken to tackle it. So with this word, I once again thanks to our guest speaker, Professor S. Ramchandran sir, Climate Change Department, and our technical advisor Sital sir, and all the members from the JEDA also, those who are very pioneer in organizing this program. And I think this is not for a day program. We can have this approach across the years, in every month, every week, and everything. And we have to come.
Sir, we have received many comments and questions from participants.
Yes.
So some of them would like to interact with Professor.
Yes, sure.
So I will request Ms. Shamini Nath, if you can ask your question. Then Dr. Priya Datta, John Matthew, Mr. John Matthew. Yeah, please, Shamini. Yeah, please ask your question. Hello, Miss Shamini, would you like to ask the question?
Yes, sir. I want to ask a question.
Yes, go ahead.
Hello.
Yes, go ahead.
Sir, I want to ask you that the rate of pollution is much greater in the tropics and Mediterranean, but we see that the ozone has occurred in folds. Why tropical stratospheric ozone layer is not depleting despite being the highest pollutant in the region?
Okay. When you say ozone layer, we are referring to the ozone that is present in the stratosphere, which is very high. The amount of gases, some molecules that are present are significantly higher than in the troposphere. when you are referring to pollution, urban pollution or atmospheric pollution, you are referring to the ozone that is present in the lower altitudes. Now, as I said very clearly, that ozone above us is actually good. The ozone near us is actually bad. No, it's not good. But what is happening is the ozone near us is increasing because of the very pollution that you mentioned just. So it is not a tropics or the high altitudes or any other location. Anywhere increase in the anthropogenic emissions are occurring, ozone is increasing in the troposphere. And this increase increase or the rates of increase have changed or different. But overall, in the last 20-30 years, atmospheric ozone levels have increased across the globe almost.
Mr. John, please ask your question, John. Or Kamala Vardu, Mr. Prakash Kamble.
Okay, I have the questions that are visible in my chats. So I will try to answer those questions also.
Yes.
Okay.
Yeah.
Okay. So is it Kamala Vardu? Okay. So the one of the questions is that considering the fact that ozone hole is found in Antarctic, how it can directly affect humans. So as we saw in the presentation, that the hole is formed in Antarctic, but in the mid and the high altitudes, ozone is lower than what it was years ago, and hence the reduction can increase the biologically active radiation, amount of radiation that is reaching the Earth surface, hence has a direct impact on the humans. We also saw that the erythemal levels have been increasing in the last 40 years. And then there's also a question by the same person, namely the stratospheric events, coming event, the ozone depletion can be seen, or where do they affect? And that was the example that we saw in 2002, for example, how the one of the events that happened because of this phenomenon, namely the sudden stratospheric warming, etc., split the ozone hole into two halves and then change the concentrations in a different way than it was the ozone. And Kamala Vardu has asked a few questions. For example, one of the questions is more than 50% of the population is using refrigerators and air conditioners. How can we reduce pollution and get cancer? At the outset, I like to remind and also mention that what Sahu addressed in his comments, that the chlorofluorocarbons, those are used in a variety of industries, including refrigerators, etc., air conditioners, they have been phased out. In present, in their place, now we are using what is called as the hydrofluorocarbon, which contain hydrogen, chlorine, and fluorine and all. Now, they have less lifetimes. Then the ozone depleting potentials, these are actually much smaller or insignificant as compared to the chlorofluorocarbons. These are made up of like hydrogen, carbon, and next. Now, so like happened with the increase in the chlorofluorocarbons leading to ozone depletion, and then the Vienna Convention, Montreal Protocol, etc. Similarly, the very convention of the Montreal Protocol also took into account, suppose if these ions, what we call as the HFCs, they keep on increasing, what will happen to the ozone and the Earth's temperature or climate change? So subsequent to that, there was a meeting in Kigali, which is now called as the Kigali Amendment, which happened in 2016. So there is also a cap on the amount of HFCs that can be put into the atmosphere. So there are measures that are being taken across the globe, and you will be happy to know, be surprised to know that Montreal Protocol is the only protocol, PT, or the document that has been signed by all the countries in the world, the home and only treaty. So then the next question is, India has worst ozone air pollution compared to other. So as I answered before, we are saying pollution, we are referring to ozone that is present in the lower altitudes. The pollution is more, the ozone is going to be. And okay, one more person has asked, does warming happen in the high air or altitude? Also has a role in deepening a role or not. This is not the principal cause of ozone depletion is not the principal cause of climate change. So warming happening at the higher altitudes is greenhouse gas emissions. And then the next question is black carbon aerosols. These are, when you say long lived, these are not long lived. The residence time of these species, carbon noxious aerosols, is from a few hours to only a week in the earth. They don't get transported that much in the higher altitudes. I think those are all the questions. Yeah. Yes, Shwetalji, I'm done with.
Sir, one thing one participant would like to understand that if emission is say emission of ozone depletion or depleting substance is mainly in tropical region, but why ozone hole happens in polar region?
Okay. First, we should understand that much of the human race is actually in the northern hemisphere and compared to the southern hemisphere. But however, we see that the depletion is more in southern hemisphere, southern polar region, when compared to even the northern polar region. So first thing is the transport of the ozone that is produced. Even before the ozone depletion occurs, etc., the transport of the ozone that is produced in the tropics, the northern movement of the ozone-rich air is more stronger and significant when compared to the southern hemisphere. This is one reason. Second reason is the lifetimes of these species are much longer. So they, even though if they get equally distributed, because of the conditions that exist in the Antarctic, namely temperatures that are lower than minus 78 degrees centigrade for more than 6 months a year, when compared to the Arctic polar region, which is only 2 months a year, where the ozone levels are higher compared to Antarctic. So the decrease that happens is more significant in Antarctic when compared to Arctic.
Right, sir. Thank you, sir. If any participant would like to ask, we can take one more question and then we can finish today's webinar.
Yes.
So there are also some technical question like why 1980 was taken as a baseline in Vienna Convention. So I think the answer should be that it was the time when the entire research was published, and I think 3 scientists were also awarded Nobel Peace Prize for discovering this ozone hole in I think 97 something. So there is always administrative baseline which is required to create the consensus among the stakeholders, and therefore the 1980 was the baseline, and then the progress of the country were I think then monitored based on those set of data.
This has I'll tell you an interesting story. Three scientists who were awarded the Nobel Prize in Atmospheric Chemistry in 1995, namely Crutzen, Maria Molina, and Sherwood Rowland. They conducted a laboratory experiment in 1975. Then they found that if chlorofluorocarbons are present in the atmosphere, in these temperatures, the ozone can get reduced, ozone can get depleted. But so this was the proof of concept, as you can call that. If this thing happens, ozone can be reduced in the atmosphere. So subsequently, ozone hole per se as a reduction in ozone was discovered in the year 1985 by British Antarctic Survey, which was responsible for measuring ozone in Antarctic, etc. So between 1985, so 1980 and all, the ozone was normal, so that is taken as a baseline. And interestingly, 10 years later, exactly 10 years later, these three scientists who predicted already that ozone, because of this, ozone will decrease. In 1995, they were awarded the Nobel Prize for Chemistry.
Yes, sir. Yes, sir. Very important story. So thank you very much, Professor Ramchandran, for enlightening us on this important topic. And we also have put the entire recording of today's webinar on our YouTube channel of the Climate Change Department. And I think similar is also shown live on a Facebook page of Good Cost. Sir, correct me if I'm wrong. So thank you all. Sir, we have got a very good response and also comments that you can also see in the chat box from across the corners for giving us this nice presentation and understanding. So thank you all. Thank you very much. Thank you.
Thank you, Shetal Bhai, for nicely coordinating this program.
Thank you
so much, and thank you to your team also.
Sir, we got a very good response from community science centers across the state in today's webinar. They also have greatly benefited from the delivery.
Yes. No, in fact, we have received the message from out of the state also. So I got the 2-3 message, and also our live Twitter is also going on. So the large number of good response is also coming from there. So I think everybody has a concern about these things. And I think our presentations and deliberations by Mr. Ramchandran has gone to the right way and the right platform. So on behalf of Climate Change Department, Gujarat Council on Science and Technology, and the Department of Science and Technology, Government of Gujarat, we thank you, Professor Ramchandran sir, and we seek your support and cooperation in all our scientific programs.
Thank you very much. Always.
Thank you. Thank you so much.
Thank you, sir. Thank you.